All right, so today, let us go to section 6.1. Get your textbooks there. And obviously the title, chapter 6, circular motion and other applications of Newton's laws, and 6.1, Newton's second law. For a particle in uniform circular motion. Basically, we're looking at the force that's exerted on a particle as it turns around. It's the force that keeps that object moving around in a circle. Cut the force off, then the particle is going to go in whatever direction it was going to. So there's a case really of Newton's second law and Newton's first law simultaneously. The object is moving around the circle at constant speed, Newton's first law. There's no force on the outside, generally. And then there's a force on the inside by tension, by friction, by gravity, by some kind of force that keeps it twirling around in a circle. Uniform circular motion, huh? I used to give a demonstration. I had a pail of water turning over my head, and everybody's like, ah, tripping out. Ah. But, hey, it's a great example of the object's going to stay in the water's going to stay in the pail because it's going at a constant speed around me. And 100% success on that. But yeah, it's nice to see these things. Okay, so as we said last time, an object moving around a circle constant speed is said to be in uniform circular motion. And there is a center seeking acceleration, which means centripetal acceleration. And that acceleration is caused by some net force, because we know from first principles, from Newton's second law, that a net force is responsible for creating and causing a net acceleration in the system. Two masses moving with an acceleration is caused by some net force in that particular direction. There is centrifugal is not really a force. And the reason is because there's no balancing force that goes the opposite direction. So the question was, what's the difference between centripetal and centrifugal? Many people get centrifugal, the fake force that is centrifugal force, with inertia. So they've misunderstood that when you take away the force that's going to the center of the circle, that you have a force going in the opposite direction. That's centrifugal. It really isn't. It's just velocity, really. It's just the object's going to tend to go in that particular direction. Have you ever been in a car and you're rounding a turn, you're in a seatbelt, you're not going to move anywhere because you're secure in the object. But then if like you have some bags or something in the next seat, it's going to go forward. Or as you're turning, it starts to slip because there's no force to keep that stable, and it's going to go in the direction of the velocity it was going in the first place. Much like when you put yourself on put your foot on the brakes, you're going to go forward because you already were going that direction, and vice versa. I have that backwards. If you put on the gas, you go backwards because you're already at rest, and so you go opposite direction. So if an object is not secure in that frame, it's going to go in the direction that it was originally going to go in the first place. The bag of groceries are going to go in. They're going to want to go in a straight line as you go around the circle. So the picture of that is you're going around a turn like this. You feel a centripetal force. You're secure in your seat. You're going to be turning to the left as you round that turn, but your groceries are going to want to go, in that direction of constant speed because there's no force to hold it down. So in short order, there is no real centrifugal force, because that would mean that you're trying to say that, you have this centripetal and then you have this so-called CF or centrifugal. Well, there's nothing that creates that. All you have on the outside here is a constant speed. So there's nothing that can even set this up, vectorially or otherwise. The reason why you have this is because the velocity is changing, creates an acceleration. Well, the reason why there's an acceleration at all is because there's a source for that acceleration. That's a centripetal force. There's no source for this. So it's called a really fictitious force. But it's kind of used in higher levels of physics. We actually had to deal with that in grad school. We had the Coriolis force, centrifugal force, and we had to resolve. We had to use all of these different forces to describe a system, particular system. But in essence, it's irrelevant here. So, oops. Hopefully that answers your question. Okay. Acceleration. Very good question, because people get that, misconstrued. It's caused, so the centripetal acceleration is caused by some net force due to such forces like tension, friction, gravity. This is going to be important because when we get to chapter 13, we're just going to take what we're doing here and expanding it out to a real life application. Okay, Earth on Moon. If we look at from the perspective of the Earth, the reason why the moon is going around in circles is because of the force of gravity that the Earth exerts on the moon. And it keeps the moon going around at a constant rotation all the time. That's why you can predict where the moon's going to be at certain points, when it's going to be a lunar eclipse, because that speed rotating around the source of the central force, which is the Earth, is going to keep the moon going constant. And if we were looking from the moon's perspective, the Earth is going around the moon. So, and if you're in the center of mass, as I was saying last time, you're going to see both. So it's all the same thing, but the orbits are really just an extension of this concept of centripetal motion, or circular motion. Gravity or any other force. And we will start seeing the applications of energy with this concept. Yeah, as we go to orbits, Kepler's laws and that sort of stuff. So we'll start seeing that tomorrow. So we have the circle. So we have this velocity, the vector is changing direction, so therefore there's an acceleration. We saw that geometrically, the velocity vector is changing direction, and therefore the acceleration, we show that the acceleration is going to be pointing to the center. This is the reason for the centripetal, kind of see why it happens. So again, this speed is constant in magnitude, it changes direction, and every time, at every moment, we have this centripetal acceleration that we have derived as v squared over r. Like I was saying before, by Newton's second law, we know so you can't have an acceleration without a net force, right? So you have two forces or multiple forces, but whichever force is larger in that system, that's where your system's going to accelerate to. So the only force in question here is towards the center, maybe caused by friction. If you're in Indianapolis 500, you're rounding a turn. The reason why you're rounding it is because of friction going to the center. We'll see some examples today. Therefore, the direction of the net force is the direction of net acceleration, or just acceleration. They're dependent on each other. You know that this is a directly dependent equation. Therefore, again, so as the centripetal acceleration goes to center, so does the source of that acceleration, which is the force, which is also to the center. And it's just an easy substitution. So that's the centripetal force equation. Now, as with anything, this is like, a net force. This net force is centripetal, but there can be certain forces that make up this centripetal force, just like we were doing in our free body problems. T minus mg or T minus friction force equals ma. The same thing's going to go here. But you have to figure out what forces make up this net force of mv squared over r. So again, let's say I have a, string, I'm pulling it and I'm here and I have my string and this is the ground. And then I have a tennis ball at the end of the string, some radius r from the center. And of course you can see vectorially, well, yes, vectorially as well as intuitively that the force is going to go to the center as you round it around this circle. It's the ground. If I cut this off, then by Newton's first law, it's just going to keep on going like this. But since it's ground, gravity takes over, it's just going to, go like that. It's going to start off with as a horizontal projectile, and gravity is going to increase it in the y direction and hit the ground. So Newton's second in the center, Newton's first always around the circle, not unless we have some outside force that's going to increase that velocity around the circle, which we've seen last time, section 4 or 5, and which we'll probably see tomorrow again as in non-uniform circular motion. It's the same thing. It's the application of the same concept. Okay, so this is basically first tendency, object of motion stays in that motion, and there's no more second. Okay. So let's go to quick quiz 6.1, if you will. And the bottom of page 138. You all there? Okay, well, orientation matters. You're riding on a Ferris wheel that is rotating with constant speed. The car in which you are riding always maintains its correct upward orientation. It does not invert. What is the direction of the normal force on you from the seat when you're at the top of the wheel? So you've been on Ferris wheels before, I presume, and your car is up here. So no force from the surface. Oops. So it's going to be pointing like that, upward. And from the same choices, what is the direction of the net force on you when you, what is the direction of the normal force on you from the seat when you are at the top of the wheel? And then from the same choices, what is the direction of the net force on you when you are at the top of the wheel? So the net force in the system, okay, so this is you, normal force up, mg, and centripetal is down. And so the centripetal is the net force, so the net force will be pointing downward in this case, provided you are on top of the Ferris wheel, because to be up here, that would be bad, head rush. But so that's that. So you got it upward and down. Questions? Okay, let's go through some examples here. Quickly, but too quickly. So example 6.1, we have the conical pendulum. So with this pendulum that, rotates in a circle, and orientation. So we have the string here comes out like that. And so the roof here is providing the tension, source of tension. And then we got this ball. Okay, so it's going around in a circle like that. And they want you to find the speed, the velocity around the circle, the constant speed. So the string of length L, some arbitrary speed V, and radius R. So the radius R. So you can just imagine this plane is flat and this guy's kind of going around. And so this tension is at some angle theta here. And so our job is to find V. So in order to find V, we understand that the centripetal force, which causes the centripetal acceleration, is equal to mv squared over r. So in order to get this expression here, we have to get the expression for force first, and then we can get the velocity here, because we want to have the velocity term being the last thing that we consider, because that's the ultimate goal, is to get velocity. So before we get that, we have to get the force that makes that, right? Because this is a net force equation. And so generally what we do in order to get the forces that make up the net force is we use free body diagrams. So in order to get the centripetal force, must draw free body diagram to determine FC. And by now, tension theta, this is T cosine, both positives. And we have this guy here, this is mass, so mv. So the force that makes up the centripetal force is T sine theta, right? So therefore, what we have then is T sine theta is equal to m v squared over r. And if we, go in terms of our previous logic of dissecting this in terms of free body diagrams, we get all the forces in the x and y direction. So this is the x-axis equals this. And then we have T cosine theta minus mg equals 0. So our goal again is to get V. So we have to wipe out T in some kind of way. We have to deal with this first in order to get the ultimate goal. So best way to do that is let's get an expression for T from the second equation, substitute it back in there, and then just as you can see an example, and then solve for B. Just wanted to be explicit about it. Okay, so T is equal to mg over cosine. And that means we have mg over cosine theta. Sine theta equals mv squared over r. That becomes g tangent theta. I'm not going too fast. Sine over cosine. And then solve for v. So that's the trick, because there's going to be some force that makes up the centripetal force. So use your free body diagram logic for all these type of questions. Get an expression workable. Solve for the variable. In this case, velocity could be radius. V squared is rg tan theta, and this is going to be square root rg tan theta, and that's it. But as we see, you can leave it like this or do r in terms of L, right? So if we did it, same thing, we have string of length L, and this, this would be L cosine theta. This is L sine. Then, yeah, L sine theta is r, the radius. So we can just say L sine theta g tangent theta, and that's the final answer. Right. Questions there? So I think they even said, well, they just said find expression. Right. Went further and did it in terms of L. Use all the variables. Okay, if there's no questions, I want to skip to example 6.3, where we have this car, going around a circle here, 1,500 kilogram car moving on a flat horizontal road negotiates a curve as shown in figure 6.4a. If the radius of the curve is 35 meters and the coefficient of static friction between the tires and dry pavement is 0.523, find the maximum speed the car can have and still make the turn successfully. So we have mass 1,500 and then mu s. Okay, static friction because it's kinetic and you got slippage. All right, so and then what we're to find expression for v. So the maximum velocity is the point, basically short, simple way of thinking about that. The maximum velocity that they mention here is going to be at the maximum radius, because velocity is going to be proportional to radius and centripetal acceleration is going to be a constant. So how do we know that? AC v squared over r. V is equal to square root of r AC. Holding this guy constant, V is proportional to, well, square root of r, but V is proportional to r. So the maximum velocity will be at maximum radius. So at that point of maximum radius, that's the point of maximum static friction. If you exceed that, then we have slippage. It's going to skid out. It's going to go from the boundary of static friction to kinetic friction. Okay, is this why people spin slings around before releasing them to hit? Yeah, pretty much. For going back to, I think, the previous example, that's pretty much why. You are doing it, not to get a higher speed per se, but you want to get a maximum tension, so you get a good little swing going on, and boom, and it goes off at maximum speed. Let's scroll up to the list of knowns. Sorry, I didn't see your previous. You mean this guy here? List of knowns? Okay. But yeah, it's just because all those things are dependent on each other. F is proportional to V. F equals mv squared over r. Okay. Yeah. So maximum velocity at maximum radius is at point car will be skidding outward, et cetera, et cetera. And we did the proof. So at that point, we know that the centripetal force is going to be equal to the friction force. Can we prove that? Well, if we then look at the perspective of the picture here, we have normal force here and weight down there, and then the static friction going into the center of the circle. It doesn't matter if you had Fs going left or right, just perspective. So Fs is equal to mu Sn, and then that's going to be equal to mv squared over r. That's the only force in question, or at least the only force that makes up the centripetal force. So again, it's best to always approach these guys in terms of free body diagrams, get the force that makes up the centripetal force, and solve for here are unknown. So then doing it standard way, it's Fs equals USN equals mv squared over r, Fy. So what we want to do, because this is the guy, again, the most important thing, we want to get the velocity. Let's get an expression for normal force. Why do we even like think in terms of that? Because we know by diagramming this via free body diagram and putting it into your force equations, we're going to get an expression for normal force. That normal force is going to be equal to something that we can substitute in, makes our life easier. Could we solve it like this? Yes, we can, but it's simplified. You know, we're looking for simplification. So when it's kinetic friction, it's going to point out of the circle. No, when it's kinetic friction, the car is going to skid. There is no force that's going to point outside of the circle. Kinetic friction is going to always be towards the center of the circle. A source of friction is going to always be towards that center. So there's not going to be a case where there's going to be a opposite force from centripetal, the so-called centrifugal. Yeah, because there really isn't enough data, information, vectors to even make up something that can go that way. One way of putting that. So N equals to mg. And then we have mu s mg equals v squared over r. And then we just have v squared equals to r mu sg. Therefore v. And that's your expression. Put in numbers as needed. Oh, and they do it. Of course, that. All right. Got to have numbers here. So V equals to, 35 times 0.523 times, that comes out to be, well, 13.4. Meters per second. Okay. So let's run, you know, through these guys. This is type of day, minimum day. So in this example, we have a velocity of 16.4 meters per second, because the civil engineer wants to create a banked curve such that cars will go around at 16.4 meters per second, no matter what, the rain, snow, sleet, and the radius of the curve is 35. So what is the angle that he must design the bank curved at in order to maintain this speed? So real life problem here. So one, as common, we want to find the force that makes up the centripetal. Sorry, got confused in the previous problem. The static friction was, yeah, static friction is centripetal force, yes. Correct, because that's any force, that's the only force that points to the center. And that would be the static. Find force that causes the centripetal force via FBDs. Okay, so we have this banked situation, so normal forces like that. And then we have a weight coming down. And then we have, so this is theta, you know, opposite that geometry will prove that this is theta. And y in cosine theta, and then that's going to be in sine theta. So in sine theta is going to be towards the center of the circle, right? That's our perspective. So that's the force that makes up FC, and then we just deal with the rest. In sine theta equals that. And then in cosine theta minus mg equals 0. So yeah, so let's get an expression for n again. V is the most important guy here. Mg over cosine theta. And then we can replace this expression from the second into the first here. And thus we have mg over cosine theta sine theta. And then we have that. So this is going to be sine over cosine tangent. Yeah, we've got to find the angle there. Okay, so then we have g tangent theta like that equals v squared over r. Equals v squared over gr. And therefore theta is equal to inverse tangent v squared over gr. And then you can put your numbers in there, and velocity was 16.4. That comes out to roughly, see there, 27.6. So the civil engineer must design a ramp at this angle to get his conditions met. Physics going into engineering. Yeah. Any questions? Do want to do that last example. Maybe rushed, 5 minutes or something, but I could if you guys wanted that. Set it up and finish it tomorrow. But any questions on this? You see the logic, with start to finish. If you do, great. Okay. Yeah, we're trying to find the angle. Always free body diagrams, because you want to see what force makes up that net centripetal force. And the rest is pretty standard. So I'll set this up and see how far this goes. Example 6.5, this is a good one because you can see why you're going to feel weightless at the top of a circle. You go on a roller coaster ride, I felt that every time, and we used to do a project to Six Flags project in physics, and they would feel that too, it prove that too. In this problem, the pilot goes around the loop, radius 2.7 kilometers, he's flying, and you know, speed is 225. So like Goliath, if you've ever been on the Goliath ride, you feel so like crushed at the bottom, like because that normal force is just kicking you. Prove it numerically, and then at the top, you know, you feel very light. But mass M, radius 2.7 kilometers. Okay, so guy's going like this, constant speed around, magnitude is constant, radius R. Determine the force at the bottom, free body diagrams. Okay, so here we have this normal force at the bottom, and then his weight. And those forces, this end bottom is going to be the source of, well, both of them together are going to make up the net force that points to the center. The other examples, we just have one force that makes up the net. In this case, it's going to be two, just like any problem, it could be two or many. So again, this is all y direction. Normal force at the bottom minus mg equals mv squared over r. And then can solve for the normal force at the bottom, as we see in the problem there. That normal force at the bottom is going to be the force at the bottom that you feel. And you can see in the next part of the example, if you can continue, that's going to be the normal force at the top, and it's going to be less. But I'll just leave it there. Any questions on that setup? So yeah, I'll assign homework, you know, tonight for next Wednesday, and our first skills test will be next Thursday. Okay. That will do it. All right, guys, I will thank you. See you tomorrow.
Bye, Mr. Kelly.
Bye, Leo. See ya.